Okay. Welcome to this 5th week of our course. So last week was the week of integrals. So we built a theory of integration that is valid for any measure space, in particular for a probability space. Okay? So our notation for integral was, so if you have a measure space, our notation for the integral of x is this, right? And if we don't write anything, this is always the full set. You can put the arguments of those functions, I mean the argument of x, and what you can write here is a d mu of omega, like you do in Riemann integration, right? You have dx. And sometimes it is just better to write it in a different way, like this. Mu of d omega, which means what? So it gives an intuitive way to, a nice way to interpret what this integral is. So this integral is really like a multiplication or sum of those products, where d omega is an infinitesimal set, measurable set. Okay, of course, it is just an explanation, just an interpretation. So this is like the weight of the set, which is very small. So this set is very small, and it's around omega. Okay, so therefore we look at the value of the function at omega, and we multiply it by the weight assigned to this infinitesimal set around omega. So you can give such an interpretation. And in the probabilistic setting, we call it the expected value. So expected value of x, you can put square brackets. If you're not sure what your probability measure is, you can put p. And all this means is that this is the integral of x with respect to p. And in the above notation, I can write it as p d omega omega. Okay? They all mean the same thing whenever this integral is well-defined. Okay? Well-defined means what? So if you have a numerical random variable, it's either its positive part has to be integrable or the negative part has to be integrable. In the complex valued case, the real and imaginary parts must be integrable. Okay? And by definition of a complex number, the real and imaginary parts are just real numbers. They cannot take the value plus or minus infinity. So in that case, you need to have an integrable real part and integrable imaginary part. But in particular for positive functions, namely functions taking values in 0 to plus infinity, including 0 and plus infinity, we never have any issues. The integral is always well-defined, and it is okay if the integral is plus infinity. Okay? Because we define the integral of a positive function as the limit of the integrals of its approximating functions that are simple and positive. And by the monotonicity of the integral for simple positive functions, so those integrals form an increasing sequence of positive numbers. Therefore, they always have a limit which is inside the set 0 to plus infinity, including plus infinity. So for positive functions, the integral is always well-defined. Okay? But if it is equal to plus infinity, we don't say it is an integrable function. Okay? Integrability means the finiteness of the value of the integral. Okay? In addition to being well-defined, of course. So what I'd like to do is to start by a recall or more of a restatement of the results that we proved last week, okay, in the probabilistic language. So I'm going to call it a proposition, but there's no proof of it because everything is proved last week. I will just specialize into the case of probability spaces. So omega f p is a probability space. So what is special about a probability space is that the probability measure is a finite measure, okay? Therefore, if you integrate a constant function, what is the value of it? What is the expected value of a constant? Itself, right? If you integrate a deterministic function, its expected value is itself, okay? The reason is that a constant function is a simple function. Therefore, its integral is just the constant times the mu, or the measure of the whole space, which is 1 in the case of a probability space. Therefore, in the probabilistic setting, constants are always integrable. So if C is a real number, then expected value of C is itself. In particular, constants are integrable. Of course, finite constants. Okay. So this is not a general result, right? In the general measure theoretic setting, the integral of a constant can be plus infinity or minus infinity if the measure is an infinite measure, right? If the measure assigned to omega is infinity, then the integral of a constant function is not finite. Okay. So what else do we know? So if x is a positive random variable, then what do we have? The expected value of it is also positive. And if you have expected value of it equals 0, this is if and only if x equals 0 almost surely. So now I'm writing almost surely instead of almost everywhere, because we are in the probabilistic setting, almost surely. And you can say P almost surely if you would like to emphasize that you're using P. And that's a probabilistic statement, meaning that the probability that x is 0 is 1. And this is by the insensitivity of integral that we discussed last time. Okay? Insensitivity means null sets don't matter in probability theory. So if you have, if you had x equals 0, the integral would be just 0. But if you have a non-negative function, a positive function whose integral is 0, you can conclude that x is 0, but up to almost sure equality. So you can have non-zero values on a set of measures 0, probability 0. Okay? What else? So x is less than y implies expected value x less than expected value of y whenever one of the following holds. So one is, or maybe I should write them as bullets like this. So for instance, if they're positive, for sure we have monotonicity, the integrals are well defined. What else? So if we can make sure the integrals exist, then we have no problem with the definitions of expected value of x and expected value of y. And moreover, we can just assume one of them is integrable. So expected value of x. So x is integrable, or y is integrable. So whenever you have one property, one of these two conditions, you have the existence of the integral for both. So this implies the second one. But cases that whenever you have positivity of the functions, you don't worry about the existence of integrals, so you automatically have monotonicity. So in other words, you have monotonicity whenever the integrals make sense, whenever the expectations make sense. Okay? What else? We have linearity, right? again, we have linearity in the positive case and in the integrable case. So let's say we have xy, random variables, and AB that are reals. Okay? So we have expected value of ax plus by equals expected value a times the expected value of x plus b times expected value of y whenever one of the following holds. For instance, when xy are positive and ab are positive, and x and y are integrable and real valued, and AB are reals. So I don't write just integrable, but I also write it's in L1, which also assumes real valuedness. So when I write just L1 without saying R bar or anything, this means they're integrable plus they're real valued. I want real valuedness because I want ax plus by to make sense for every omega. Okay, that's why. But you can also add a third condition which says ax plus by is well defined and x and y are integrable. You can also say that. So whenever you can write this expression down, there is no problem. Okay? Okay. So if we have x and y that are equal almost surely, then expected value of x equals expected value of y whenever, again, this expression makes sense. Whenever this expression makes sense, for instance, x and y are positive or the integrals exist. Well, if one exists, I think the other exists as well. So we should say just or. So these are kind of ordinary results, and there are also limit results. So remember we had monotone convergence theorem, which says if you have x1, x2, etc., that are increasing with a limit x, then the expected value of x is equal to the limit of the expected values of xn's. So just you need to assume these are measurable. So these are random variables, okay? That's the only assumption. And you also have the integrals are increasing. Maybe I should have written this the other way. So expected value x1, expected value x2, etc., with a limit expected value x. And there was a series form of it. So if you have xn, positive random variable, for every n, then the expected value of the series of this random variables is equal to the sum of the expected values of xn's. And let me also say that I don't really care what kind of brackets or parentheses that you use. It's not really important. And sometimes we just omit them because there is no room for confusion, right? So when you don't put any brackets or anything, we still understand that this is expected value of x. So you can omit them whenever there is no confusion. Okay. Anyway, what else do we know? So this was the series form of monotone convergence theorem. Okay, there was Fatou's lemma, right? There was Fatou's lemma. Let's say this. So if you have, let's say, xn that is positive for each n, and that's a random variable, so then we have expected value of the lim inf of xn's is less than the lim inf of expected values. And since we don't assume anything about monotonicity or the existence of limit, we don't know if a limit exists, but the lim inf always exists. Okay? And there was the reverse Fatou's lemma, which I'm not going to repeat, but that was about lim sup. And the important convergence result was dominated convergence theorem. So you have xn, okay, and for each n, so the limit exists, okay, and there is some y that is integrable such that xn is between minus n plus y for all n. So that is the condition of being dominated by some random variable y, okay, integrable random variable. So in that case, we have the same conclusion with monotone convergence theorem, not this type of monotone conclusion, but that the expected value of x is the limit of the expected values of xn's. Okay. So a special case is the so-called bounded convergence theorem, which wasn't mentioned in the last week, because, okay, let me first write bounded convergence theorem. So in the bounded convergence theorem, we have the same stuff. The limit exists. What we assume is that there is a constant such that the sequence is bounded by this constant in absolute values for all n. And of course, for all omega. So that's an omega by omega inequality, okay? And here, so xn of omega is between minus n plus c for every n and for every omega, okay? So C is a bound. And so the only thing to check is that this constant C is an integrable one. Is a constant integrable? Yes, we just said it at the beginning, right? Constants are integrable. So in the probabilistic setting, we have this corollary to the dominated convergence theorem. So if you have a bounded sequence like this, you have the conclusion of dominated convergence theorem. There are actually a few more properties that I'd like to state separately and leave as exercises for you. Okay, so suppose you have two random variables, okay? Random variables, and their expectations exist. So if we have x less than y, we can certainly multiply them by some indicator, right? And now the inequality is preserved, so we can take the expected value. So there is nothing wrong about this, right? So for every a. What is also true is that we have the converse up to this almost sure version. So if you have expected value of x less than expected value of y, of course you cannot conclude that x is less than y. But if you have expected value of x over any set, over any measurable set, and you have expected value of x over that set is less than the expected value of y over that set, for every measurable set A, then you can conclude indeed that x is less than y almost surely. Okay? So that is maybe a property that is in the spirit of this insensitivity result, right? So of course we don't have the converse here, right? But if you have the order over any region, over any A, like there, we can have the converse and say that x is less than y almost surely. Okay. So there is one nice inequality. So there are many nice inequalities in probability theory. So one is the Markov inequality. Okay. So if you have a positive random variable and a constant epsilon, so you can relate the probability that x is greater than epsilon and the expected value of x in the following way. So let's write expected value of x as expected value of x over the region x greater than epsilon and over the region x less than epsilon. Since x is greater than epsilon here, I can bound it by expected value of epsilon times the indicator of x greater than epsilon by monotonicity. Where is it? Monotonicity here, right? And this is just a positive quantity, so I can lower bound it by 0. So what is this expected value of a constant? I can take it out. And what is the expected value of the indicator? It's the probability that x is greater than epsilon. So you can write it as follows. Probability that x is greater than epsilon is less equal expected value of x over epsilon for every epsilon. So this is called Markov's inequality. So we talked about expected value of x, right? So expected value, expectation, or sometimes mean. Okay? So if you raise x to power n and look at the expected value of this is called the nth moment of x. So the first moment is the mean. You have second, third, fourth moments. And if you look at the random variable minus its mean, this is a new random variable. Of course, assume that expected value is finite and so on. Okay? So, but now this random variable has mean 0, right? So that's a centered version So centered version of x. So if you look at the second moment of this, this is called the what? Of course, the variance, right? Variance of x. And you can check that this is equal to expected value of x squared minus square of the expected value of x. Assume x is, let's say, real valued and integrable so that we don't have any issues, okay? Though in this case, variance can still be plus infinity. But it's okay. So as long as this expression is well defined, when you square it, this is always a positive random variable, so its expectation always exists. What you can prove is that the variance of ax plus b is a square variance x, meaning that variance does not change under shifts. And if you multiply the random variable by some constant, it is reflected by a square in the end result. And what you can also prove is that there is Chebyshev's inequality, which is derived from Markov's inequality. So I'm not going to prove it. This is listed as a homework exercise. So the probability that now x is, the deviation of x from its mean is greater than epsilon, with probability being less than variance of x over epsilon squared. That's a very simple consequence of Markov's inequality. So again, let's assume x is in L1 and epsilon is 0, strictly positive. And let me also excuse somewhere what we call the standard deviation. The square root of this is called standard deviation, okay? So standard deviation. So I guess you all knew them. At some point, you learned them. But it is also nice to see that they are valid in this general framework, right? On any probability space. Okay, any questions? Everything fine so far? Okay. So then we can talk about something new. Okay? So that is the last part of our second chapter, distributions of random variables. And after finishing this section, we will be done with the topics of the midterm, okay? We're not going to do anything else before the midterm. So whenever we finish this section, we're going to stop lecturing, and you will just have some time to digest the topics before the midterm, which is going to happen in 2 weeks, okay? Okay. So far we discussed expected values and integrals, okay? And in some special cases, we were able to calculate them. For instance, when the measure is the Dirac measure, when the measure is the counting measure, or in general, when the measure is a discrete one. Finitely many points, you attach masses on each point, etc., etc. Discrete measures, okay? The other case was when you use the Lebesgue measure on the real line, So the Lebesgue integral with respect to the Lebesgue measure on the real line coincides with the Riemann integral, as we discussed last week. So, but these are the two cases where you can really calculate things in terms of the stuff that you know. Okay? How do we do calculations in general? If we're given one random variable, what is the key property of it which we can use in the calculations of mean, variance, etc., etc., or some probabilities? Can we calculate the exact probability, exact value of this probability? Not the bound, but the exact value. So all these are related with the distribution of a random variable. So we need to introduce a new concept, okay, which is the distribution of a random variable. And we're going to introduce it in a very general setting, namely the setting where the random variable can take values in an abstract measurable space. It doesn't have to be a numerical or real valued random variable. So even if the expected value of a random variable is not defined at all because it's not a numerical one, we can still talk about its distribution. And distribution is probabilities about the random variable. Okay? So let's fix some measure space, okay? And some measurable space with no measure. So we have a random variable from omega to e. So let me say measurable function. So here's the picture. So there is omega here, f and mu, and there is e and script e. So x takes this omega and maps it to the point x of omega. That's a function from omega to e. That's what it does. Now, we have a measure in the domain of x. Okay? We don't have a measure here. But this is the quantity of interest. We are interested in this random variable. We would like to calculate probabilities about x. How are we going to do that? What are interesting events about x? What is an event about x? Do you remember the sigma algebra generated by x? What was the definition of it? What kind of events do we look at? Sorry? With respect to which x is measurable, right? And what was the definition of it? Sorry? Yeah, so it is a sigma algebra. You're right. But we even have a special structure, a concrete structure of the events about x. Very simple structure. So if you were dealing with a random variable, what kind of events would you look at? So let's say x is a Poisson random variable. Tell me an event about this Poisson random variable x. Just an example. What is an event about x? It is integer valued, so can you name an event about x? The event that x is equal to 0, is equal to 5, is between 0 and 5. So in fact, if you have a real valued random variable, you would look at an arbitrary Borel set and look at the event that x takes values in that Borel set, right? So in other words, since you have a measurable space here, you can take an arbitrary measurable set, D, okay, and look at the event that x takes values in the set D. which is the preimage of D under X. So this is the set of omegas for which X of omega is in D. So this is X is in D, or X preimage D. What we know is that this is in F. This is in F because X is measurable. By the definition of measurability, for every D in script E, the event that X takes values in D is an F measurable set. Therefore, you can define a function, a set function, as follows. The probability or the measure that X takes values in D that's a function on the sigma algebra on E, and it takes positive values, right? And in fact, let's write it as a lemma. Nu is a measure on E script E. Just check it yourself, right? Just the definition of measure, countable additivity. So you can check nu of empty set is the mu of X is an empty set, but X is an empty set is the empty set. Therefore, mu of empty set is 0. Things like that. Just check the definition of a measure. So let's rewrite it in a different way. So we say nu of D is equal to mu of this set. Okay? Let me write it as X inverse D. So we're going to write it as mu and the composition of this with X inverse, the preimage, not the inverse function, at D. Okay? Nu mu of X preimage is called the image measure of image measure of mu under X. And if mu is a probability measure, then we say nu, which is this, is, we say that is the distribution of X under P. So that is the definition of image measure or distribution. So distribution is nothing but a measure in the set where the random variable takes values in. Okay? That's the correct definition and the one definition of distribution. Okay? So distribution is nothing but the probabilities that X takes values in certain sets. Collection of those probabilities, or it is the measure which is a function which is seen as a function of the set in this space. Okay? So now we have a measure here. The image measure, the distribution, or the induced measure, sometimes called. So now we have a measure here. So here's a remark. So if mu is a probability measure, then the distribution nu is also a probability measure. Probability. But on the other space, right? Indeed, just look at the nu of E. So E is the full set. It is the probability that X takes values in E. And X always takes values in E. So I'm not saying anything here. So this is like something happens. So which is 1. And some notation is that, so we write X is distributed by this distribution for the case, this is, let's say, mu of X inverse, okay? So another remark. So now I'd like to relate this concept with the similar concept that you know from your earlier courses. Do you remember any concept whose name includes the word distribution? Blah, blah, distribution, blah, blah. Cumulative distribution function, for instance, right? So you all know it. If you have you don't know it, okay. Okay, but many of you know it, okay? But even if you don't know it, it's okay. So let's recall what it was, okay? First of all, what is the idea? The idea is that recall that a sigma finite measure on E script E is uniquely determined by its values on a pi system P such that it generates script E. So, for instance, let mu equals P is a probability so that nu, which is the distribution of X under P, is a probability. So it's a finite measure, so it's a sigma finite measure, right? So assume, let's say E script E is the real line, or maybe the extended real line. So what is a pi system that generates the Borel-Sigma algebra on the extended real line? How did we define the Borel-Sigma algebra on the extended real line? What are the intervals that we started with?
Closed intervals with infinity included.
Minus infinity to somewhere, maybe. Or plus infinity down to somewhere. Okay? Let's use the minus infinity to somewhere. Let P, script P, be the set of intervals of this form, where B is a real number. Okay? So nu is determined by its values on script P, because it's a pi system that generates the Borel-Sigma algebra. And as a consequence of the monotone class theorem, in the first chapter, we proved that if you have two probability measures, two finite measures, two sigma finite measures, so if they agree on a pi system, if they agree on intervals like that, then they must agree on the whole sigma algebra generated by the pi system. That was a very important characterization or uniqueness property. So what we can do is to look at the values of nu over those intervals. So what does that mean? x is between minus infinity and b. But now, the form of the sets that we look at have only one parameter. Those sets have only one parameter, which is the right-hand point, right? The left-hand point is always minus infinity. So in fact, I can call it a function of this right-hand point b. So let's define it for every b. So this is the cumulative distribution function. This is the cumulative distribution function. So f is called the cumulative distribution function of x under p, let's say. Okay? So that's why in elementary courses, people talk so much about cumulative distribution functions. Since they don't have the measure theoretic background, they cannot talk about distributions, but they can talk about cumulative distribution functions, which characterize distributions. So if we know so sometimes we just abbreviate it as CDF, the CDF of x, then we know the distribution of x. Okay? And as an exercise, check that f is increasing, meaning that if you have b1 less than b2, this implies fb1 less than fb2. Okay. F is right continuous. Okay. So this means if you look at f of x at x going to b, down, we approach from the right. This limit coincides with the value of f at point b. So that's the right limit, that's the value of it. So if you look at the limit of f as x goes down to minus infinity, this is the probability that x is exactly minus infinity. And if you look at the limit of f as x goes to plus infinity, this is going to give you the probability that x is between minus infinity and plus infinity excluded. So it doesn't have to be 1 if you have an extended real valued random variable, okay? Just be careful about it. So in elementary courses, usually we deal with just real valued random variables, and this limit equals 1. But if there's a strictly positive probability of taking the value plus infinity, then you don't have this equals 1. And similarly, if you have a real valued random variable, of course, this has probability 0, so this limit will be 0. But in general, if you have an extended real valued random variable, the probability that x is equal to minus infinity can be strictly positive. Yes?
I couldn't understand the right thing, because why did we exclude the case plus infinity?
So you need to show it. You need to show it, right? Maybe using sequential continuity. Okay? So if you take a sequence of xn's approaching to plus infinity, okay, write down what fxn is, okay? Fxn is a probability, and since xn's increase to plus infinity, okay, you will have sequential continuity, so you can check this. So this is all exercise. So let's check the time, and it's time to give a break.